Hello everyone, welcome to the group demonstration of our robot SULIS. Our project goal was to develop a cost-effective, bio-inspired robot to navigate and maneuver through unstructured rubble and underground terrain, delivering a direct communication line and water aid to trapped survivors following an earthquake. This led to the development of SULIS, our centipede-inspired robot aptly named after the Celtic goddess of water. Our goal for this demonstration is to provide proof of concept by exhibiting the first steps of this development process, including a functioning modular design with specific design aspects intended to assist movement across the unstructured terrain. This project was motivated by the increasing occurrences of natural disasters worldwide due to climate change, often leading to the loss of human lives. The first 72 hours post-earthquake are crucial to locate survivors and provide first aid. Although current robotic solutions, including drones and large ground robots, have been used to locate survivors, their applications are limited in scenarios where victims are hard to locate underground and in tight spaces.
We investigated multiple methods of natural locomotion inspired by snakes, salamanders, and centipedes. Due to the centipede's ability to adapt and navigate through challenging environments, we decided that biomimicry of this animal would prove successful, with a modular design with multiple legs working according to a central pattern generator, CPG, network. This is especially important because it leads to the production of a rhythmic leg motion that stems from the morphological properties of the centipede's body and requires minimal computation. The unpredictable environment that SULIS operates in provides several challenges. The robot may need to traverse a variety of surfaces such as soft soil, steep inclines, and large steps. Therefore, a robust body and adaptable locomotion system is needed. The centipede-inspired leg and body structure provides increased flexibility and stability, accommodating for locomotion through the debris left behind following an earthquake. The multiple legs, spread out like a centipede, allows for increased stability, enabling SULIS to navigate without getting stuck in crevices and debris, an environment in which traditional wheeled robots may struggle. Centipede locomotion is particularly inspiring due to its adaptability in different terrains. We aim to encompass these essential features in SULIS as its environment can change rapidly with post-earthquake tremors and aftershocks. The unstructured environment also poses challenges for sensors, power systems, and communication methods. GPS signals are not strong enough for robot navigation underground. Therefore, we considered the incorporation of acoustic sensors and night vision sensors to locate survivors. The use of multiple modular segments increased driving power and performance stability whilst maintaining a flexible body for locomotion through tight spaces and rubble. A tethered power system provided extra stability for the robot and its communication and water delivery lines, alongside providing a direct line to the survivor once it reached its goal.
Our prototype consists of 3 modules, easily detachable and reattachable, that are interconnected via universal joint, allowing flexibility across the entire robot in turning maneuver and overall traversing complex terrains. The main structure is segregated into the head and body modules, with the power supply, a DC brushless motor situated in the head alongside the main gear mechanism and the breadboard. Wireless Arduino board resides in the second module to alleviate the weight in the head module. In the belly of each undercarriage runs a power cable, adjacent to the water supply tubes, with 2 hole designs implemented in case there are multiple survivors located simultaneously to maximize on water delivering capabilities.
Ahead of designing any CAD models, the initial prototype was created from cardboard and was used to observe whether our primary leg movement concept would be successful. Once the gear mechanism was constructed, we tested out 3 individual leg designs, which included a conical shape, a filled semicircular shape, and a hollowed C-shaped leg to determine which would be the most beneficial to our overall design. As observed through the displayed video, we concluded that the curved profiles of the semicircular designs would increase the ground contact time and frictional properties, whilst being less likely to become stuck or snagged. The C-shaped leg was selected due to it being the lighter option that wouldn't be cumbersome to the overarching robot design. We tested alternative materials to develop the legs, including Ninja Flex, also known as TPU. A fin-ray-inspired leg was CAD modeled and hence printed, with increased compliance and deformation to obstacles it came into contact with, allowing the robot to climb over debris without getting stuck. Also, the soft legs are lighter and more flexible than rigid legs, which can enhance the robot's agility and efficiency. However, due to time constraints and TPU material properties, such as the release of toxic gases at high temperatures, which made it incompatible with the heat set element of our design. Therefore, we didn't implement this into our robot, but we consider it as a future development with alternatives to heat inserts.
Post-training material options and design shape, it was determined that our final leg design would incorporate two PLA printed C-shaped legs combined to form a new S-shaped design that would retain all benefits of the original shape, while the increasing ground contact time to stabilize and smoothen movement. To increase locomotion stability and imitate a closer representation of a typical CPG movement, a 90-degree angle difference was implemented to the leg rotational position that effectively created a lag between the offset of each pair of legs, which therefore kept the robot in contact with the ground for longer. A worm gear mechanism is here to help transfer the power from the main shaft to each leg in a vertical direction. The gearing ratio between the motor and shaft are designed to minimize the speed of the robot and increase the torque, so that a single 18-volt DC motor can drive SULIS easily and gives extra obstacle clearance ability.
The body itself went through multiple design iterations. It began with a Lego connection concept that would allow us to compartmentalize the following sections: electronic circuitry, motor compartment, gear mechanism, and water and power compartments. As displayed, the Lego design allowed us to deconstruct the robot simply and access alternative segments that needed attention, although this was not bio-inspired enough or compatible with the terrain due to the sharp edges and non-streamlined surface. Therefore, a second iteration was developed that conformed to the body of a centipede with low frictional surfaces to eliminate risk of snagging whilst retaining the Lego concept to simplify fabrication processes. The bottom compartment was designated to the power and water cables, as through our stakeholder meetings, the pros and cons of tethered robots were analysed, and it was determined that SULIS would be tethered regarding the water and power cables. This is because a direct power cable could provide more energy to the robot, whilst two deflated pipes would be dragged through and behind SULIS, only to be inflated with fluid, water or a saline solution, once a survivor is located, thus further reducing the weight. To secure the individual compartments, 4 stud connections were added upon each level that could attach the top and bottom compartments. We experienced difficulties when adding the shafts into the body, and therefore further divided this category and used outside screws to fasten it into place. The final adjustment was the addition of the Arduino board that was originally meant to reside within the lid of the body, but due to the Arduino board size, we've removed the lid and simply encompassed it into the body itself.
The electronic components of the robot include a gas sensor to detect carbon monoxide levels in the surrounding environment, along with a webcam and a microphone.
In order to improve the prototype, several enhancements could be considered, which we've grouped into 3 different categories: improvements to the robot's movement and behaviour, water delivery and control, and data collection. To improve the robot's locomotion in unstructured environments, the design of the legs could be altered using soft 3D printable materials such as TPU as briefly investigated, leading to smoother movement and decreased jarring. This modification would increase the robot's flexibility, durability, and ability to maneuver through tight and cluttered spaces. Furthermore, shortening the shaft's length would help obtain more compact modules that require less motor power and smoother locomotion. Upgrading to a more powerful motor with increased torque would help support the movement of different robotic modules. Moreover, to enable multi-directional movement, a pulley system could be added, and springs on either side of the universal joints would help dampen the movement. One of the robot's missions is to deliver water to survivors on site via 2 parallel inflatable tubes actuated by water pressure through designated holes at the bottom of the design. However, due to time limitations, we were unable to test the inflatable mechanism. Thus, future work could investigate the information and testing of this system. Since the robot will likely be operated by rescuers and not engineers, a control system that involves a gaming console or computer keyboard is recommended to reduce cognition load and improve ease of use. Moreover, the robot's functionality could be expanded by including additional sensors to collect key data, such as thermal cameras to locate survivors or acoustic sensors for aftershock detection. Ultimately, the robot could become autonomous.
We would like to thank Hackspace, Tech Hub, Electrical Hub, our stakeholders, and our personal tutor and lecturers for all the time and support you have dedicated to us. Make sure to keep an eye out for SULIS in the future.
Thanks
for listening.